Interplanetary dust. Interplanetary space contains many small particles referred to as interplanetary dust. Radiation pressure from the Sun sets a lower limit on the size of such dust particles. To see the origin of this limit, consider a spherical dust particle of radius R and mass density ρ. Part A, write an expression for the gravitational force exerted on this particle by the Sun, mass M, when the particle is a distance r from the Sun. Here is our particle with radius R, density ρ, at a distance r from the Sun, which has mass M. So if I write the gravitational force between the two, using Newton's law of universal gravitation, gravitational force is gravitational constant g, mass of the Sun, which is M, mass of the interplanetary dust m, divided by the radial distance squared, where the mass of the interplanetary dust particle is its mass density times its volume, assuming spherically shaped dust particles. We have 4/3 pi R cube for the volume. So we can write the gravitational force Fg to be gravitational constant g, mass of the Sun, divided by r square, mass density ρ, 4/3 pi R cube, or we can rewrite this as the gravitational force equals 4 mass density ρ g pi mass of the Sun, R cube, divided by 3r squared. So that's how we can write the gravitational force. Part B. Let L represent the luminosity of the Sun equal to the rate at which it emits energy in electromagnetic radiation. Find the force exerted on the totally absorbing particle due to solar radiation pressure, remembering that the intensity of the Sun's radiation also depends on the distance r. The relevant area is the cross-sectional area of the particle, not the total surface area of the particle. As part of your answer, explain why this is so. So here's the light coming from the Sun. You can see it hits a perpendicular cross-sectional area, which is the cross-sectional area of the particle. Now, the intensity is the power divided by perpendicular area, and the power is the luminosity of the Sun, which is capital L, and it's going to be divided by 4 pi r square, assuming that the Sun is a point source of electromagnetic waves in the universe. And that's going to be the intensity as a function of radial distance from the Sun. The perpendicular area, A perpendicular, for the particle is going to be the cross-sectional area, which is pi R square. It's the area of the circle. So we can see that the pressure, average pressure that will be inserted is the intensity I divided by the speed of light c for complete absorption, which is average value of the Poynting vector s divided by c. This is our result for complete absorption, which is the case for this interplanetary dust particle. So we can calculate the average pressure P bar is equal to the intensity L over 4 pi r square, power divided by the area divided by C, which is the force divided by the perpendicular area A, and then we can see that this force F, due to the electromagnetic wave pressure, is pi capital R squared multiplied by the intensity, which is the luminosity L, divided by 4 pi r squared c, the speed of light. Now you can see that the pi's will cancel here, and we will be left with the force due to radiation, F sub r. Let's say this is force due to radiation, is equal to luminosity times the radius r squared, L r squared, divided by 4 r squared c. So that answers part B. Part C, the mass density of a typical interplanetary dust particle is about 3000 kilograms per meter cube. Find the particle radius capital R such that the gravitational and radiation forces acting on the particle are equal in magnitude. The luminosity of the sun is 3.9 10 to 26 watts. Does your answer depend on the distance of the particle from the sun? Why or why not? Mass of the sun is 1.99 10 to 30 kilograms. So we're going to equate the gravitational force to the radiation force, Fr. So we see that the gravitational force, the answer to part A, is 4 rho g pi mass of the sun capital R cube divided by 3r square. This is equal to capital L r square divided by 4 r square c. Now we can see that the r squares will cancel. This r square will make this r cube r, and we will be left with a critical radius, capital R, equal to 3L 3 times the luminosity divided by 4 times 4 times 4, 16 density rho g, universal gravitational constant, pi, speed of light c, and mass of the sun m. This is our critical radius. We can calculate what it is for the given numbers. The critical radius r is equal to 3 times the luminosity, 3 times 3.9 10 to 26, divided by 16, density 3000 kilograms per meter cube, 6.67 10 to minus 11, gravitational constant, pi, speed of light 3 times 10 to 8, mass of the sun 1.99 10 to 30 kilograms. So this gives us a critical radius 1.9 10 to minus 7 meters, or r is equal to 0.19 micrometers. All right. And let's move on to part D. Explain why dust particles with a radius less than that found in part C are unlikely to be found in the solar system. Construct the ratio of the two force expressions found in parts A and B. Okay, let's take a look at the ratio of the radiation force to gravitational force, Fr to Fg ratio. It is capital L r square divided by 4r square c. Then we have gravitational force, 1 over the gravitational force, 3r square, 4 rho g pi, mass of the sun. This is g, capital R, cube. Now in this ratio, we see that the r squares will cancel, and then the capital R square will make the capital R cube capital R. So we can see that the force ratio Fr to Fg ratio varies as 1 over the size of the particles. 1 over the size of the particles. So if R is less than 0.19 micrometers, what happens? The radiation force will be greater than the gravitational force. If R is too small, the radiation force, this ratio increases, the radiation force will be greater than the gravitational force. That means the radiation force pushes the particles out of the solar system because it wins over the gravitational force. So such particles cannot be maintained in the solar system. So this explains why dust particles with a radius less than that found in part C are unlikely to be found in the solar system. So in this problem, we have talked about interplanetary dust. We calculated the gravitational force between the spherical dust particle and the sun for a radial distance r in part A, using the law of universal gravitation and writing the mass of the particle as density multiplied by its volume for the volume of a sphere. Then in part B, we calculated the average pressure exerted by the electromagnetic radiation coming from the sun. The intensity of the sunlight is the power per perpendicular area, which is luminosity divided by 4 pi r square for spherical waves coming out of the sun. And the perpendicular area for the particle, for the beam that hits the sun, is pi capital R squared. That's the cross-sectional area of the particle. And for complete absorption, we have mean pressure is intensity divided by the speed of light. So L over 4 pi r squared times the speed of light is the mean pressure. That is the radiation force divided by perpendicular area, which is pi r squared. So this allows us to calculate the radiation force. If the radiation force is equal to the gravitational force, then we can see that this corresponds to a critical radius of 0.19 micrometers. The ratio of radiation force to gravitational force varies as 1 over r. So if r is less than this critical value, the ratio increases and the radiation force wins over the gravitational force, pushes the interplanetary dust particles, very small dust particles, out of the solar system.